Okay, students, let's discuss about the here F block elements only. You can see, students, this is the periodic table. In this periodic table, the elements are which appear at the bottom of the periodic table is considered as the lanthanides and actinides. Lanthanides and actinides combined together we can call as the F block elements only. Lanthanides and actinides combined together we can call as the F block elements only. You know, wherever F block element starts from the, look at this is 3D series, 4D series, 5D series and 6D series one. What I'm just considering from the here the generally fourth period only. Generally start from the sixth and seventh period containing of the lanthanides and actinides only. So the elements are which appear at the bottom of the period table is called as the F block elements only. In the F block elements are then when you consider the elements of the after coming lanthanum, whatever coming after lanthanum is have the properties similar like a lanthanum only. It means that one is there here cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium only. So whatever the elements are, these 14 elements are possible here. Here 14 is there, here 14 is there. So these elements have the properties similar like a lanthanum. That's what they call as the lanthanide series only. So the elements is called actinides only. So this is called actinides. Thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium only. So what I mean there here, this are the whatever the elements are coming after actinum have the similar property like a actinum. That's called actinides only. So remember here, this students remember here, consider that these elements are which appear at the bottom of the periodic table is called F block elements only. In this F block element, most of the elements are man-made elements only. Most of the elements are man-made elements and they are the radioactive elements only. What is the radioactive stands for nothing but some elements are emits the radiation without any external effect only. You can see very clearly there now uranium is for the preparation of some nuclear power plant on the can use only. So you can see the lanthanides, actinides. Lanthanides are also called as a 4F series only. Why they are called 4F series? But the differentiating electron into the F orbital only. The differentiating electron into the F orbital is called 4F series only. So if differentiating electron into the 5F orbital is called as a 5F series only. That's nothing but actinides only. Lanthanides and actinides only. So students, that today I'm going to discuss some more focus about the F block elements only. So look at in this one is there here. What is the F block? Is there no F block elements also called as a inert transition metals only. Generally F block elements also called as inert transition elements only. Why they are called inert transition metals means that we consider the last differentiating electron into the inner shell n-2 F orbital only. So let's look at the idea. So what I mean the differentiating electron into the n-2 F orbital only. N-2 F orbital. So this is called as the inner transition elements only. You can see the general electronic configuration of F block elements are there no n-2 F0 to 14. It means that one is there no 14 elements are possible in the F block elements only. n-1 D0 to 1. NS2 only. So what I mean there the last electron into the inner shell is there now. This called is the outermost shell is there now. Penultimate shell is an ultimate shell only. So what I mean there n-2 orbital last electron enters now. That's called as a inner transition metals only. Look at that. This is also called general lanthanides called 4F series only. 4F inner transition metals also known as the lanthanides only. 4F nothing but the differentiating electron in 4F orbital. Inner shell is called lanthanides. So it's called 4F orbital is called lanthanide series only. And also you can see the 5F orbital is called as the actinide series only. Whenever differentiating electron enters the 4F orbital, you can remember lanthanides. Whenever differentiating electron to 5F orbital, you can call as the actinides only. You can call actinides only. The general electronic configuration of lanthanides are there. So what if in the lanthanides the differentiating electron into the F orbital? I mentioned clearly the last electron into the F orbital only. You can say very clearly lanthanum is there. No, lanthanum is not a F block element only, but the properties are very similar to lanthanum. That's why we place here. So lanthanum atomic number 57. Electronic configuration is xenon 6s2 5d1. Cerium you can see the last differentiating electron of 4f1 orbital 4f1. So what I mean there here next one is praseodymium. What I mean there here you can see the f3 4f3 6s2. Next one is there here the neodymium is there no f4 6s2. Next one is there here the promethium 5 6s2. Okay, next one is there no samarium 4f6 6s2 only. Next one is there no europium Europium is there 4f7 6s2. Gadolinium, you can remember the gadolinium, europium, ytterbium, lutetium. They will exhibit some exceptional electronic configuration. Once again repeat, the europium, gadolinium, erbium, lutetium, they exhibit some exceptional electronic configuration only. Do you know where like copper and chromium is there, no? How they exhibit exceptional electronic configuration? That is you can remember also. You can remember here the elements having stable electronic configurations are europium, gadolinium, erbium, lutetium only. We can see very clearly the outermost orbital contain 3 electrons. As you can see the 2 plus 1, 6s2 5d1 only. So what about this 2 plus 1 electrons are, no? So generally lanthanides having the common oxidation state is plus 3 only. General lanthanum having the common oxidation state is the plus 3 only. That's remember plus 3 only. So what about the plus 3? You can also very clear what about the atomic rate, ionic rate. You can see when you're moving down of the what about the atomic rate decreases only. And also you can see very clearly is there, no, the atomic radius not increase regularly because nothing but a lanthanide contraction. Because nothing but lanthanide contraction. Sorry. First coming to the atomic and ionic radius of the lanthanides only. So we will discuss much more about the lanthanide contractions only. So what happens as the atomic number increases, each screening is elements containing of the one proton and one electron in the one more electron in the fourth orbital. Along with the electrons, what I mean the protons also will come only. So what I mean there is a competition between the screening effect and the repulsion there. But 4f orbital having less screening effect. So what I mean they cannot screen properly from the outermost orbital from nucleus only. So what I mean the nucleus force of attraction increases, the electrons are pulled very close to the nucleus. That's the reason why atomic size suddenly decreases. This type of contraction is called as the observe this kind of the properties observed after lanthanum. That's called as lanthanide contractions only. The observed cloud is called lanthanide contractions only. Because what I mean there's decreasing of there because of lanthanide contraction, the elements atomic size very close also. You can see very clearly here. The element atomic radius are very close only. We cannot see any large change in the atomic radius also. Next one is then here. Look at the one more very important point is the consequence of lanthanide contraction. What are the consequences happen with lanthanide contractions? Is there, no? This is there is a close resemblance of the 4D and 5D transition series. We can see very clear what I mean there. The atomic size is very close between the 4D and 5D transition series only because of the power of orbitals are fields only. Next one is the ionization energy of the 5D transition series is higher than when compared to 3D and 4D. Do you know very well, whenever you listen the word lanthanide contraction, decreasing of atomic size, whenever atomic size decreases, nuclear force of attraction on the outermost orbital increases, so electrons are not easily removable only. Next one is the difficult to separation of lanthanides only because of very similar atomic size, very similar chemical properties are no. It is very difficult to separate the lanthanides only. Very difficult to separate the lanthanides only. This is called lanthanide contractions only. You can see very clearly atomic nucleus only. So what happens there? This nucleus has some strong force of attraction in this electron. Do you know very well f orbital have no fused structure only. Because of fused structure, f orbital cannot screen the whatever the electrons present in the outermost orbital only. Suppose here f orbital is there, they can screen the electrons what are present in outermost orbital. Because of poor shielding effect, what happens the atomic size suddenly decrease. This is called as a lanthanide contraction only. Once I'm repeating them, because of poor shielding effect, atomic size of elements are suddenly decrease called lanthanide contractions only. This is called as a lanthanide contractions only. Next one is here the one more thing is there now here color compounds only. Do you know very well is there now many lanthanides ions are color compounds only. Both are solid and insolid solution phase also. While general atomic elements are color nothing because of the FF transition is possible only. Because of FF transition possible, that's the reason why atomic elements are have a partial filled electrons. One point I want to mention very clearly: whenever you saw some unpaired electrons are there, vacant f orbitals are there, that element can exhibit the coloring property. Whenever you saw the no vacant orbital is electrons complete filled, they are the colorless only. So what I mean they are considered the lanthanum La plus 3, lutetium plus 3 only. You can see very clear is there no here. Lanthanum is there no here 4s2 6s2 5d1 only. Whenever you remove these 3 electrons, no electrons are there. So because no electrons are there, nothing but a complete fill of the electrons are there. This type of electronic configuration never ever exhibit any color compound. You can see on 4f0. And also you can see lutetium also +3 only. So what is lutetium containing xenon 4f14 only. No vacant orbital, no general vacant orbital. So because of no vacant orbital, no free electron is there, no, these compounds are never ever exhibit any coloring properties only. Lanthanum because of lack of the f orbital, lutetium because of complete fill of the f orbital is there, no, these two compounds are never ever exhibit any coloring properties only. Next, oxidation state only. Remember, whenever you remember the oxidation state 1.1, how many electrons needed to required to lose particular metal in order to attain the stability only. So what I mean, generally lanthanides lose 3 electrons in order to get the stable electronic configuration only. You can see very clear idea is then here 2 plus 1. Whenever 3 electrons lost, lanthanum becomes the La plus 3. Whenever become La plus 3, direct in the noble gas configurations only. And also you can see the most common, you can see they lose 3 electrons only. Most commonly they can lose the 3 electrons only. So what I mean, the general oxidation state of the lanthanides are +3 only. General oxidation state of the lanthanides are +3 only. Remember, the most stable oxidation +3 is there, no, lanthanum, gadolinium, lutetium only. Okay, no, lanthanum, gadolinium, lutetium is there, no, it exhibit more stable electronic configuration +3 only. You know wherever is the why that happen means you can see very clearly. Lanthanum become to the 4f0. Gadolinium is there. You can go gadolinium is there. No, what happens there? Whenever lose 3 electrons, become 4f7. Half filled orbital become more stable only. And also you can see very clear there are many elements also here. They have the, because of attaining the stable electronic configuration, they become more stable only. But one exception, remember, cerium, terbium, they can exhibit the +4 oxidation that is more stable only. Once again repeating that, you can remember cerium and terbium, because of +4, it shows +4 oxidation only. Sometimes you can see the occasionally you can see the +2 and +4 oxidate in the solution solid phase only. Generally most stable oxidate is +3 only. Generally most stable oxidate is +3 only. Their irregularity arises mainly the extra stability of the empty and half filled orbital only. Sometimes mentioned some elements exhibit +3 oxidate, some is +2, some is +4. Why these kind of oxidation states appear? Nothing but because of attainment of extra stability. Some elements, you know, very is then you can see very clearly here the gadolinium. If gadolinium lose 3 electrons, it is half filled electronic configuration only. So what I mean there, it lose 3 electrons only. Suppose if you go for some elements are then here, just imagine here the lutetium. If it loses 3 electrons are then becomes the 4f14 complete electronic stable electronic configuration only. You can see erbium is then if it loses 2 electrons it becomes the 4f14. What of 4f14? It becomes more stable on electronic configuration. So in order to attain the stable electronic configuration, some F-block elements exhibit the variable oxidation states. Next one is, remember here you can see the most common oxidative lanthanides are +3. Hence the ions of +2 oxidates tend to be changed to +3 only. What I mean is now some ion +2 oxidate also they can lose one more electron, they become +3 oxidate only. Look at the one more point is, remember students, this is for question for you. Why samarium +2, uranium +2, erbium +3 ions in the solutions are good reducing agent, but in the aqueous solution C++4 is a good oxidizing agent. So this is question for you. Why samarium +2, uranium +2, erbium +2 ions are solutions are good reducing agent, but aqueous solution of cerium +3 good oxidizing agent. Why? So you have to find the answer and say, look at there, what is cerium, what is mentioned +4 oxidate only. So what is +4 oxidate here? They consider that whenever these 2 electrons, 4 electrons last, what I mean there, it becomes 4f0 only, 4f0. So what I mean they try to attain the electrons from some other elements only. Next one is chemical properties of lanthanides only. I said very clearly the common oxidation state for lanthanides are +3 only. But metals are combined with hydrogen when generally they heat with gas only. So what happens when you take the metal, when you heat it with the gas, they form a hydrate. So you can get a clear idea is here. You can see very clearly when our lanthanides are heat with the react with the acids, they can produce hydrogen gas only. When our lanthanides are react with halogen, they form a metallic trihalides only. You know very well, oxidation state is three compounds. Next one, lanthanides are react with the water, they form a lanthanum hydroxide only along with hydrogen gas. Whenever lanthanum react with carbon, they form a lanthanide carbide only. Whenever lanthanum react with nitrogen, they form a lanthanide nitrates only. Whenever lanthanide react with sulfur, they form a Ln2S3 only. These kind of chemical compounds are possible whenever lanthanum react with the different types of the compounds only. Next, coming to the here,